Thank you. And thank you everybody for joining at this webinar on this, I would say, weird or uncommon topic. But before talking about it, I would like to say something about me. So you know me. I have a PhD in mathematics, so I have been studying a lot on video and image authentication. And I had worked also with University of Florence in project related to the reverse engineering of multimedia contents, both with the European Commission and DARPA projects. And I am also the co-author of several papers in topics related to multimedia forensics. And meanwhile, I took experience as an expert witness in Italy in topics and issues related to multimedia forensics. So in my experience, I saw the different points of view, the researchers that think in a specific way. On the other side, we have the authority, you have the judge that is expecting an answer. You need to apply technology in real cases. So the scenario is different every time. So you need to find a solution by applying scientific method. So the topic of uncertainty in the forensic assessment is everywhere. Okay, it's very general. It involves several fields. Okay, you can work with images, with audio, but also other fields like if you work with DNA, with fingerprints. There are some common principles that require a lot of attention. Okay? And I think it's really challenging to deal with this topic because on one side, if we only speak about examples and we treat examples, then maybe it's hard to discover the big view, the theory behind the principles. Okay. But if we speak about the theory, then it can be very, very hard to go in details and to fit the theory in any examples. So in this webinar, I will try to do something in the middle. Okay. And so we start from a very general scenario in which, as forensic practitioners, we are asked by an authority, a party, or someone, okay, to examine or compare material. So a general situation, independent of the fields in which you are involved, you generally have some recovered material or unknown material, okay, and some reference material, and you have to decide something, which relation is between these two material, okay? So a common situation is that we are asked to decide between two competing propositions. That depends on the specific circumstances. So we have to decide, for instance, if two samples, the unknown material and the reference material belong to the same sample. Okay? So we perform our analysis, and in the end, we have to assess the strength of our finding. So we have to provide an output to the judge. Okay, this output must be scientifically sound, but in some way, for all of us that have experience in the field, there are a lot of issues because nothing is black and white all the time, and we have to take decisions. Okay. So just a disclaimer before starting, this webinar is not about how things should be done because the topic is very general. We belong to different fields. We belong to different countries, so there are different regulamentations. We have different cultures. So depending on these factors, in the end, there is no unique way to do things, okay? But, however, there is a common field in which that we are going to treat today that is trying to deepen the understanding of the different role played by each piece of information that is involved in the forensic assessment. Okay, so we acquire the material, we extract features, we use tools, we combine them together, we provide the outcome, we interpret the finding. Okay, and furthermore, deepen the distance between the intuition that we have about, probability. Just to say, when we read the probability that this image is a deep fake is 90%. Okay, what does this mean? Is the intuition that we receive from this sentence correct and correspond to a real probability? Okay, so we'll try to understand which is the true achievable statements that we can reach based on available information. Okay, and the principles that we are going to share can be used in several scenarios. Okay, just some examples of questions that we can be asked to solve, and in which these principles that we are going to discuss can be applied. For instance, determine if a person in a CCTV is the same as a specific reference person, okay? Or determine if a car is compatible with a specific car model, or if an image has a specific life cycle, for instance, if it has been synthetically generated, if two voices correspond to the same person. But as I said in the beginning, it's not only about multimedia. Anytime we have to compare samples, in some way we can apply some specific principles and avoid some specific mistakes. So let's start from examples, and then we try to, through the example, to go into the theory, understand the main principles that can be applied everywhere. So let's consider this example in which we have a video. In this video, there is this subject that is using this rifle, okay? And we have a reference rifle that has been found, and we are asked to examine these items and to determine whether the rifle in the video is the same rifle on the reference picture. So one thing that is immediate here is that we have two competing hypotheses, and we have to decide between one of them. Or the two rifles are the same rifle, or they are different rifles. Okay? So every time you have an assessment, it is good to determine which are the two competing hypotheses between which we have to decide. Okay? These two competing hypotheses can be found often, maybe always, even if the question is not defined exactly like this. Okay, let's make this example. Decide, help address if the image is synthetically generated. So one hypothesis is that the image is synthetically generated. On the other side, we have that the image is not synthetically generated. If we pose the question like this, for instance, the alternative hypothesis is that the image can be, for instance, camera native, but maybe can also be a camera native image that has been exchanged through social media. It doesn't seem so important, but it is extremely important how we describe the question. And because the question introduced these two competitive hypotheses, okay, that are fundamental to decide which is the proper methodology and how to assess the findings. So now I don't know how it works in different countries, but I can say, based on my experience, that in Italy, sometimes the judge, the authority, expects something like this. Expect that the forensic experts say something like, okay, it's synthetically generated. And the judge says, are you sure? And of course, the expert is very confident with his answer, maybe putting a number like 99%. And then the judge is satisfied and has his answer, the answer that he wanted. And he is almost sure that the probability of error is very, very low. But in the real world, we know that there are a lot of factors that can affect the assessment. Let's see which are the main, and then we'll try to see which are the principles to deal with them. So first, the limited quality of the material. For those of us who work with images and videos, sometimes we have to decide whether the scar on the face of the person is the same of the suspect, but the face is 10 pixels. So you have to decide if that strange value in the pixel is a scar, is compatible with the scar. So this is the first limitation. The second is that in most cases, we don't have, or we have a limited background information. We'll see that this is extremely relevant to determining the strength of the evidence and the probability of something, okay? But that in most cases, this is not available, but we will discuss this later, okay? Then we have tools when we use software to analyze things, to compare faces, to compare voices, to compare material, to analyze statistics in data. We have tools that maybe have been published. So there is scientific research behind them. So we know the performance, we know the limitation of these tools. So how to manage, for instance, if we have a system that is known to have an error rate of 1%, can we say that the probability of error is 1%? This is a question we'd like to answer today. But we have also to say that even if we use a very good tool, in some scenario, the hypotheses in which these tools work are not completely satisfied, or we don't know if they are satisfied. So the forensic expert is also required to determine and to assess if they can use the tool and which is the expected effectiveness of the tool. Okay. For instance, just to make an example that we will use during the webinar, if we have a system that is trained on a specific population, let's say a speaker identification system that is trained on Italians, can it, even if it is a perfect, whatever it means, can we use to distinguish two Chinese people? Okay, of course, we don't know, but yeah, it's something that we should consider a lot before using it. So how can we deal with these issues? We will start from a very easy example to understand which are the technical limitations that cannot be overcome. So let's consider a dream, okay? We have a face identification tool, okay? In some way, it's like an oracle, okay? That is, it has been tested on 2 billion people. You give 2 pictures and it says if they are the same person, okay? It has been tested on 2 million people. It has proved to have an accuracy of 100%. So every time it has been tested, it never failed. Okay, let's imagine this tool may exist. We know it can't, but let's imagine. So, okay, we take these 2 faces, we analyze them, and the tool is saying, okay, positive matching, all compared features match. So I can go in front of the judge and say, okay, the tool says that they are the same person. And which is the probability of error? Oh, the tool never committed any mistake until now. So can we say which is the probability that these 2 people are the same person? This is maybe the best case ever. Okay? But even in this case, we can't, because we miss some information that directly affects the probability. Let's imagine, for instance, if this girl has a twin. So it means that if she has only one twin, maybe the probability is 50%, just to say something, because it can be her or the twin. And what if there are many people who look very similar to the girl? So which is the probability? We can't say it. And why we can't say it? Because we miss a piece of information that is what we will call later background information. Okay? And we have to say that in most cases, you don't have this information available. So now keep this in mind, okay? And let's try to go closer to the reality. And let's make a more real example, an example that is closer to the reality. Because when we use tools commit mistakes. So let's consider a tool that is affected by error. What is the impact of this error on the finding and on the strength of our finding. Let's make an easy example. Please, for the experts of the technical stuff, I'm going to tell, this is a very simplified representation. I will skip several things, okay? Just because we have to stay in the middle between the theory, the example, to understand everything, okay? So let's keep it simple for now, but try to understand which is the principle. Let's consider a breath analyzer. You are stopped, you make the test. If you drank too much, you expect to get a positive, and you're done, okay? But this breath analyzer is not perfect. It can commit mistakes. So we have some common response that can be described in a table like this. So for instance, if you're drunk, the tool is expected to find you 99% of the cases. So you get a positive 99% of the time, but you can be very, very lucky. In 1% of the case, even if you're drunk, you get a negative and you're safe. And if you're sober, most of the time you get a negative, but you can be a bit unlucky and you get a positive 2% of the time. So this means that the tool has been trained and tested, okay? And these are the performance estimated from the breath analyzer. These values, just to be on the same page, have a name, okay? They are called true positive, false negative, and true negative, okay? True is used to say that the prediction corresponds to the real situation, okay? Positive is if the response is positive rather than negative, okay? So we would like to have a tool that has 100% of true positive and true negative and never commit mistake. So in this case, we have a tool that 1-2% of the time commits a mistake. So just as a little insight on which are the principles behind this estimation, okay? So how a breath analyzer works? I don't know in the detail, okay, but we have to understand the principle of a classifier in some way, because it is deciding if you are in a class or in another, if you are in one of the proposition or in the other, okay? So we can immediately find the link between the questions and the tool. So in the end, this tool is estimating something, okay, a feature, an indicator of something. If this feature is too high, you get a positive, okay? Otherwise, you get a negative. So how can we build this tool? This tool can be built like this. You need two populations, let's say sobers and drunks, and then you see which is the value of this feature that split these two distribution with the lowest error possible. So for instance, in this case, if we decide this threshold here, okay, we decide that the tool provides a positive when the feature extracted is above 2. Otherwise, you get a negative. So what happens here? It happens that we have the characteristics of drunk people, okay, that in some cases are below the threshold. These people will get a negative even if they are drunk. And vice versa, we have sober people, but there are a few of them that in some cases get a positive. So when we use the breath analyzer, we will have a percentage of true positive and true negative that are the part of the drunk over the threshold and the part of the sober below the threshold. And then we also have some errors that are the false positive and the false negative. Okay, so now we develop the tool. Okay, you can imagine the breath analyzer, but you can imagine a deepfake detector. You can imagine anything that distinguishes between two classes. Okay, so now we developed the breath analyzer. We discovered that the breath analyzer has an error rate of 1% and 2%. Let's sell this breath analyzer into different countries, Waterland and Whiskeyland. In Waterland, people are not drinking a lot. They are almost alcohol-free. Okay? So they stop drinking, almost. Okay. On the other side, in whiskey land, they found a way to produce a very, very good whiskey. So they love it and they keep drinking and they drink a lot. Okay. So we use, the police officer is using the same breath analyzer in these two countries. We expect a tool that is committing 1–2% of error. Okay, let's see what happens. We are in Waterland. 10,000 people are pulled over. And in this town, since people is not drinking so much, we have that only 1% of the people is on the road with too much alcohol. Okay, so what we expect to find? We have only 100 drunk people, because it's 1% of 10,000. And the remaining people are sober. Okay, I test them all. So I'm using my breath analyzer. So how many positive I will get from the breath analyzer? I expect 99% of the drunk. So 99% of 100 is 99. And 2% of the sober, because sometimes, unfortunately, even a sober gets a positive. So I get 99 drunk people, 99 positive from drunk, and almost 200 from sober. So in the end, after analyzing 10,000 people, I will get 300 positive. Now, if I'm a forensic expert, forget that we are talking about breath analyzer and people drinking, but you have a test, you get a positive, you want to know which is the probability that the person is drunk or belong to a proposition, given the fact that you get a positive. In this case, which is the probability? We got 300 positive, but only 100 was drunk. So the probability that given a positive, a person is really drunk is 33%. So it means that most of the time you're committing a mistake, but the tool has a 1 or 2% of error rate. So sounds counterintuitive. Let's make the same test in Whiskeyland. In Whiskeyland, I stopped the same number of people, just to make the example easy. But in Whiskeyland, people is drinking much more. So we have 10% of the people that is on the road with too much alcohol. So what we expect in this case, we have 1,000 drunk people, because it's 10%, and the remaining are sober. I apply exactly the same tool. So 99% of the drunk people are found as positive. So I get 990 positive, but also 180 positive belonging from the sober. So altogether, they are more than 1,000 positives. Now, in this case, which is the probability, given a positive, that the person was really drunk? It's the number of drunk divided by the number of positive. In this case, it's 84%. Very, very different. So I'm using the same tool that has the same performance in a different place, and the expectation of the probability of being drunk given a positive is very different. So why is that? Which is the difference? Which causes this huge difference? Only one piece of information. That is that in Waterland, 1% of the people is on the road with too much alcohol, while in Waterland, 10%. But if you are the police officer and you are testing people, you don't know this information. So moving to our cases, the forensic practitioner, in most cases, when we use the tool, we don't have this piece of information. That is a piece of the background information. So as a summary, remember that in most cases, we cannot achieve the probability of the proposition. So if the proposition is this image a deepfake? I cannot answer as the probability of being a deepfake is 95%. In most cases, I mean, we never say never, and we never say in all the cases, okay, but in most cases, the general trend is this, because we miss a piece of information. And even the probability of one proposition, given the finding, that is, this image is, the probability that this image is a deep fake, given the output of this tool, is this percentage, cannot be determined if we don't have this background information. But now in the breath analyzer, background information was something that is very simple, is a number. Okay? While in real cases, we can imagine how complex is the background information. Okay, so this background information is generally unavailable, or in some cases, it's partially available. And we'll see when it is partially available what we can do with that. Okay, but for now, please consider that it is unavailable. So if we say like this, it seems that we cannot do anything, okay, because we cannot get the probability. But there is something we can say. With the test, keep considering the breath analyzer, we can say, we can provide two answers. The first is, how likely I get a positive if you drink too much? And the test said that is 99% because it was tested. And how likely I can get a positive when somebody didn't drink too much? Again, 2%. So the contrast between these two values provides the so-called evidential strength. The larger the contrast, the higher the strength of evidence. So let's try to put all these ingredients in a more general framework that can be applied in, I don't want to say all, but in most of the cases that we can deal with. In all these scenarios, we have these ingredients. We have two competing hypotheses. Different speakers, same speaker, okay? Same rifle, different rifles, okay? The image is a deep fake, the image is not a deep fake, okay? So we have this H0 and H1. Sometimes they are called null hypothesis or the other alternative hypothesis. Okay, don't focus on this, but just remember we have two competing hypotheses. In this case, following the breath analyzer example, the person is sober, the person is drunk. We can say not sober if we want to be technically perfect, okay? Then we have a finding. The finding in this case is the output of the tool, that is a positive or a negative. In other cases, it can be the output of a tool, that can be a discrete value, a logical value, can be a lot of things, okay? But the ingredient is the same. Then we have these two important ingredients. The first is the probability of the evidence under the first hypothesis. So let's translate in the example. Is the probability of getting a positive if you are drunk. And the other is the probability of getting a positive if you are not drunk. So these two parameters can be estimated with the tool because we have them. You remember 1%, 99% and 2%. When we compute the ratio between these two values, we achieve the so-called strength of evidence, the likelihood ratio. And then we have another piece that is the background information that we can leave apart for now because it's something that in most cases is not available. Okay? So this likelihood ratio is the key point of the strength of evidence. Okay, and if we look inside it, we can find the reasoning, the good reasoning. Okay, let's make an example. So the numerator is also called similarity or intra-source variability for those who have more experience. While the denominator, called typicality, or also inter-source variability. Let's make an example. Let's say we are talking about speaker comparison, speaker identification. Okay? And let's say we are comparing the pitch of the voices. Okay? The pitch is to say you may have a low pitch like this or a high pitch like this. Okay? So this is a feature that you can use to discriminate. So the similarity is like to say, which is the probability of having a compatible pitch under the hypothesis that you are the same speaker? Oh, intuitively, it's high, unless, I don't know, you are sick, you are angry, you are, okay, but the same speaker tends to speak with a similar pitch. But which is the probability of having the same pitch if you consider different speakers? It's lower because you have more intervariability among people. So in the end, you can compute, when you compute the likelihood ratio, we completely changed the example and the scenario, but as you can see, the principles are the same. When you need to assess the strength of your finding, you have, you don't have to do anything, but it's a good practice to reason in this way, okay? To consider the two hypotheses, to define the features, and determine the probability of your finding under the two hypotheses and compare them. So if the probability under H1 is higher, you will have a likelihood ratio that is bigger than 1. So in some way, you will support the hypothesis 1 and vice versa. Okay. So in practice, when you're required to assess the strength of the evidence, you will have your two competing propositions, your features, you extract the finding, and you assess the probability of this finding under the two hypotheses. Okay, and then based on the number that you achieve, you can say that your finding support one of the two hypotheses. So the magnitude of this likelihood ratio is strongly related to the degree of support that you can provide. Okay. And I think that my main comment when this was explained to me was, okay, but in most cases, in real cases, I cannot clearly quantify the likelihood ratio. So we discuss this in a minute, okay, because I agree. In most cases, it's hard to quantify in a perfect way the likelihood ratio. So which could be a good way to proceed in this case? Okay, and we'll discuss in a moment. But for now, just to complete this point, there are some standards and some best practices that suggest which is the verbal equivalent to be used to report the likelihood ratio in a verbal form, okay? Because you go in front of the jury, and in some way, if you say, oh, I achieve a likelihood ratio of 35, okay, then okay, we have to find a way to explain it. So here I report the scale, the verbal equivalent that is supported by MC, but this is not, we don't want to say here, this is the only way, okay? Depending on the country, the regulation, you can have different ways to explain and to describe your report. But in the end, what is important for this webinar is that the reasoning, okay, that we have two competing hypotheses, and it's like we are supporting one with respect to the other. Okay. So for instance, one very, very simple example is that if we have two competing hypotheses, like the image is created with DALL-E or the image is not created with DALL-E, and you achieve a likelihood ratio that is very, very high, like +4, we can say that we provide a strong support for the hypothesis that the image is created with DALL-E. If we achieve a likelihood ratio on the opposite side, we can provide a moderate support toward the other hypothesis, okay? So this is just one way to express results, okay? But it's not what we want to focus on right now, rather than on the reasoning, okay? Because which is the main problem? If you are lucky, you are in a good case, and you have good tools that fit the scenario, you can sometimes quantify the likelihood ratio very specifically. But in most cases, we cannot quantify it. For instance, just some of the problems. First, the unreliability of the recovered material. Let's consider the case of the scar that we were saying in the beginning. So we have to decide if it can be a scar before comparing it and computing the features and then the likelihood ratio. Okay. Is it a scar? So these affect the uncertainty of the result. In several cases, we have lack of data and non-scientific results that can be used for likelihood ratio. Let's consider keeping the example of the speaker identification. If we have some specific strange inflection that is not studied, is not, I mean, we cannot have data on everything, okay? So in that case, how can we compute the likelihood ratio if we lack of data, even if the quality of the material is high? Okay. So in these cases, an expert can subjectively assess the likelihood ratio, providing the reasoning for it. Okay, but it's important that your assessment is within your expertise, because if you're not an expert of imagery, of digital videos or digital images, maybe you can commit a mistake in saying, okay, that is a scar, if you're not aware of compression. Okay, I'm making this example because we are experts of images and videos, but I'm sure that in every field, in your field, there are cases very similar like this. Okay. So how to assess, for instance, in the case of the rifle, okay, so is that specific defect that I can find on the rifle, is that a significant, has it a discrimination power to say that it's that rifle? If I'm not an expert of weapons, I cannot say it because I don't know. Maybe for some reasons, all the rifles of that specific model has the defect, and I don't know, okay? So in some way, subjectivity is required during the analysis, but it's important to use the same reasoning, likelihood ratio, and assess it only only in cases you have expertise in the field. Otherwise, it's just intuition. And as we just saw, we shouldn't rely too much on intuition, okay, in these cases. So when we compute it, even in a subjective way, we have to take into consideration the specific question, because it really changes how we should think. Let's make the example of the rifle. Okay, so we have to decide if this is the same rifle or a different rifle. But when we say the same rifle, are we intending the same model or the exact same rifle? Because depending on this question, the reasoning is very different. Let's make the example. I compute the likelihood ratio, and the question is the same rifle? So if I'm trying to understand if it is or not the same rifle, under the hypothesis 1, it's the same model, meaning that I have to find features and evidences that are related to class characteristics extracted by this from this Mauser K98. Okay. So for instance, the length of the rifle can be a class characteristics. Okay. While on the other hypothesis, we have to consider the class characteristics extracted from different models, because maybe other rifles have a different length. Okay. But if the question is the same rifle, it means that at the numerator here, the hypothesis 1, we have to extract not class characteristic, because the length is shared by every rifle of the same model. But we have to look at defect, something that is discriminating this rifle from the class. And the class is in H0. So in H0, we will extract individual characteristics from other rifles of the same model. So this is a good way of reasoning. Okay, that's why it is important to understand the question and define clearly the question, even to avoid mistakes on our side. Okay, now we understood that we will repeat every time, okay? But it's the most important thing to be remembered. So we cannot get the probability of a proposition given the evidence, okay? Unless we have the background information that we are assuming is missing. Now it's time to understand how this piece will fit in the big puzzle. And it's time to discuss a few minutes about the Bayes theorem, because the Bayes theorem describes how we update our belief based on evidence and the way we should update our belief. Until now, we discussed about likelihood ratio here and the way in which we can compute this by tools, by subjective assessment, and so on. But when we receive the question, the judge generally expects this answer, that is the posterior odd, that is the probability, following the breath analyzer, the probability of being drunk, given a positive. But we understood that we can only get the probability of getting a positive on a drunk person. But we can compute the posterior odd if we have the prior. And that's what we did when we, in the example in Waterland and in Whiskeyland. Once we get the prior, that is the percentage, the probability of being drunk, we can also get the posterior odd. But in most cases, we don't have this information. I really like this theorem. I think I understood in this specific way. I try to explain because it's also the way in which we update our belief, or at least it's my experience. Okay, for instance, let's make this example. I meet Michelle, okay, and I have two hypotheses here, H1 and H2. I like Michelle, and H2, I don't like Michelle. So as prior odd, I have no preferences, okay? So I don't know. So I have the same probability. So this ratio is 1, okay? Now I meet Michelle, and Michelle is smiling. Okay, so I have my evidence. So which is the probability of observing a smile under the hypothesis that I like Michelle? And which is the probability of a smile under the hypothesis that I don't like Michelle? In my experience, based on my data, thank you, Michelle, for smiling. Thank you. Based on my database, internal database, I tend to prefer people that smile to me. So the probability of a smile under the hypothesis that I like Michelle is higher than under the hypothesis that I don't like Michelle. So this numerator will be higher than the denominator. And I update my belief, so the probability that I like Michelle after seeing the smile is higher than the probability that I don't like Michelle. And that's the way it works. And that's the way it should work with evidence too, okay? So we don't want to go in depth with this, okay? But if you want, this is the key. I mean, this is the key reasoning behind everything we said. Just a note on background information, because we are tempted to use it, okay, to determine the posterior probability. But my suggestion, and of course this is my experience, we have to really be cautious. Okay? First, because in some cases we're not allowed to use background information because maybe it has been used somewhere else. In some other cases, it can include a bias. Okay? And furthermore, even with background information, there is a huge subjectivity. Let's make an example. So again, the question is the same rifle or different rifles? So a piece of background information can be, okay, do we know which is the percentage of Mauser K98 that has been sold in the country? This can be useful because if we have only one rifle, oh, the prior odd is very, very big. But if we have 1 million rifles, the prior is very, very low. But even here, we have a degree of subjectivity. Because, for instance, which is the percentage of the sold rifle, but should we include also toy rifles? Because maybe it could be a toy rifle. So it would change the prior if we also consider toys. Should I consider the rifles sold in the country, in the region, in the town? We can discuss it, okay? But it changes the values. And should I compare it with the other rifles or only with other rifles that are visually different? This also can be discussed. Okay, but there is subjectivity. Okay, so a good practice, or at least a suggestion, is that in most cases, background information is not available. Okay? And even when it is available, we should consider if we need or we have to use it. Okay? So in the end, remember that we cannot assess the posterior probability. We can only compute the likelihood ratio. And we have to remember that in the expression, we don't have to fall in the error of transposing the conditional. That is, computing the likelihood ratio and expressing the posterior probability. This is a very easy example of expression. One is correct, the other is wrong by transposing the conditional. So if we have a large fresh blood stain recovered from a crime scene, and we have a DNA profiling, okay, that is corresponding to a suspect. So if I say the probability of the finding on an unknown person is the value, and this is the probability of the evidence given the hypothesis, while if I transpose the conditional and I say there is the probability of, okay, I'm committing a mistake. Okay. I mean, in some specific fields where the scenario are very controlled, where we have a lot of prior information, maybe it is possible to determine the posterior probability. But in the wild, where we have to do everything, we should just focus on the likelihood ratio. So comparing and determining the strength of evidence in the two competing hypotheses. So just to summarize, which are the good practice here? So first, clarify the two competing hypotheses. They are fundamental. You have seen that in every consideration that we made, the two hypotheses are required to decide which is the right test to do and which is the right interpretation of the finding. Verify the usability of the material, okay, this car example. And based on the hypothesis, then we decide which feature, if they are reliable, which tool, if the tools are trained on a reliable data set, the example of the speaker verification system trained on Italians and tested on Chinese people. And then we can quantify the strength of evidence. In some cases, I would say in several cases, okay, a subjective evaluation can be applied, but it's important that it's based on the expertise, because the assessment must be objective as much as possible. Okay. Then you can express the conclusion with a verbal equivalent and so on. Okay. Again, if the background information is available, manage with caution. Okay. So I would like to put everything we said in a very simple and trendy topic, that is the deepfake detection. So to understand how we should reason before interpreting a result. Okay. Now, deepfake detection is a very trendy topic. So there are a lot of tools for deepfake detection. Okay. I tried many of them just to see the output that I find, and let's check them and try to interpret them after everything we saw until now. So, first tool. The first tool Sorry, the output is in Italian, but that's the way the tool is. So the tool is saying, it analyzes the image and it is saying, it's human 52 something, it's AI 47 something. And in the end, it concludes, same probability that the image is AI or human-based. Okay. So we understand that under the forensic point of view, it is very hard to deal with this analysis because we don't know what this number is, if it's a likelihood ratio, if it's not, which is the meaning, what this system is trained on. Okay. Another tool on the same image, 99% likely AI-generated image. So this is fairer, okay, because it's likely AI-generated. So it's like the tool is confident that an image is AI-generated. But if I go in front of a judge and I produce this 99%, intuitively, he can believe that we have a low error rate. But in the end, we don't know, because we don't know, even if this is a likelihood ratio, and I'm almost certain that it is not, we cannot say the posterior probability. Another example. Same image, this tool say artificial 85%, human 15%. Who knows? Another tool, AI probability 1.3%. So this tool explicitly say probability. So this is definitely something that we should avoid when we address a forensic evaluation. Another tool, confidence. In this case, again, the tool provides a confidence. So it's not a probability, and we know it's correct to avoid probability. It's not a likelihood ratio, because to estimate a likelihood ratio, we should have the data set. And for deepfake, it's very hard to get the data set, because data set keep updating. Okay? So we have this other concept that is confidence. That is a complex meaning, has a complex meaning, and it's not a unique meaning. So in these cases, we can use, we have to interpret what confidence means in the specific tool. Again, consider a speaker identification system that is AI-based and provide a confidence. So if it provides a confidence of 99%, but again, we know that the training dataset is not reliable for the specific case, we should interpret it properly. Okay. So just to close, okay, which is the lesson learned, or at least for me in these years, the lesson I learned on this topic is that to be cautious with the probability word and try to avoid it unless you are very, very confident of what you're saying. Because in best cases, we can provide a technical likelihood supporting one of the two hypotheses. Okay? And technical mean objective or subjective, but with your expertise. Okay? In some cases, we can only address some compatibility level. For instance, if you have two objects, you have to determine if they are the same object. You need two populations, the population of the same class and different class. But in some cases, you don't find traces of the different class, so you can only determine if there are some compatibilities among elements of the same class. But in the end, you have to interpret the finding based on your expertise, so stay on your lane, the quality of the material, if the training and reference data are reliable for this specific achievement, and also the considered class involved, because let's again consider the deepfake detection system. Even if we have a deepfake detection that is perfect, but is trained on some models, if we analyze an image belonging to a new model, what should we expect? So that's where you need expertise. Okay? And that's for every fields. Okay. So I see we have some questions, because on my side, I finished. I try to give an overview on this topic that is very tough. And And I hope it was a good chance to go in depth with some good reasoning on how to approach things.